record this lecture, and I did hit the record button, so we're ready to go. So in section 5.1, ladies and gentlemen, we are going to prove identities. This is something that we touched base with a little bit in the past, way back in chapter, I'm trying to remember, was it chapter 1 or 2, way back there? But we are going to formally now show ourselves how to prove that a trigonometric expression is a valid quote identity. And in order to do so, we have to have at our disposal these valid proven identities. So we can accept all of these as being valid statements, okay, where the left side is equal to the right side for all values of the angle theta. And so we have these different identities here. We have what are called our reciprocal identities, our ratio identities, and our Pythagorean identities that basically come from the Pythagorean theorem of the right triangle. Notice for these Pythagorean identities that you could take any one of these identities and solve it for anything you want to. For instance, the first one, cosine squared theta plus sine squared theta equals 1, you could solve it for sine squared theta just by subtracting cosine squared theta from both sides, taking the square root of both sides. Notice you take the plus or minus square root of the right side. All right. And so keep that in mind. Since these are accepted, proven, valid identities, we can treat them as equations. So we can solve them for anything we want to solve them for. However, when we are being asked to prove that a trigonometric expression is a valid identity, we cannot treat it as an equation. We cannot add or subtract something from both sides or divide or multiply both sides by something. You cannot do that. What you have to basically do, ladies and gentlemen, is just work exclusively with one side. Normally, we work with only one side, and we show that that one side simplifies down to being exactly the other side. Now, whether you choose to work with the right side or the left side is entirely up to you. Generally speaking, the rule of thumb is you choose the side which looks more complicated. That's the side that you normally try to show is equal to the other side. All right. So how to prove that trigonometric expressions are valid identities? Well, on page 250 in your textbook, there is a shaded box here at the bottom of the page, and it gives you some guidelines for proving identities. Number one, it says it is usually best to work on the more complicated side first. That's not to say, ladies and gentlemen, that there are times with some identities, because they're so challenging, that you have to work maybe a little bit on the left side and a little bit on the right side and show that they meet each other at some middle ground value. Our identities are not going to be that complicated in here. For that reason, we'll choose to work exclusively with just one side and show that it is indeed the other side. Number two, look for trigonometric substitutions involving the basic identities that may help simplify things. So obviously we might have to tap into our aforementioned basic identities up here, the reciprocal, the ratio, or the Pythagorean identities to help us. Number three, look for algebraic operations such as adding fractions. Of course, whenever you add fractions together, you always need a common denominator. The distributive property or factoring may be necessary. So our factoring skills with polynomials back in algebra may come back to haunt us. Number four, if you cannot think of anything else to do, change everything into sines and cosines. Normally that helps you to resolve the issue and prove the expression as being a valid identity. Not always, but usually that's a good thing to do, is change everything into equivalent sine and cosine expressions. Number five, always keep an eye on the side you are not working with to be sure you are working toward it. In other words, you never want to lose sight of your goal. Your goal is to show that one side of your expression is going to become exactly equal to the other side. So you need to always, in the back of your mind, know what the other side is that you're aiming towards. Otherwise, you could go off into a tailspin, not knowing where you need to go or how to get there or where to get there or why to get there. Okay, so you always need to know what your ultimate goal is, ladies and gentlemen. And that's not just true with proving identities. That's true with anything in life. If you want to be successful at anything in life, you have to always know what goal in specific you are trying to achieve, and never lose sight of that goal. Let it be your compass in life, so to speak. Okay, let it always orient you day to day to day as you strive to achieve that ultimate goal. So that's not only true in trying to prove identities, but also true in general in life, certainly in being successful in college. Okay, so those are some helpful guidelines. I mean, but that aside, ladies and gentlemen, all expressions are a little bit different. And if there was a magic bullet for handling every one of them, I would give it to you, believe you me. But every assertion is a little different, and because of that, we have to maybe bring to the situation a unique approach. So trying to prove that trig expressions or identities at times can seem like trying to do like word problems in mathematics, because everyone seemingly is unique and presents its own challenges. Okay, so you know what? My best advice to all of you, if you want to get good at proving trig expressions as being valid identities, try to do as many as you can possibly do. That's the only way you're going to get good at these things, is by, through experience. And you get experience, ladies and gentlemen, by trying a whole bunch of problems. Now in section 5.1, I will probably assign, most of the odd problems here. But I strongly recommend, if you want to really, become sharp at proving identities, I would try to do some, if not all, the even problems too. Seriously. That way, ladies and gentlemen, if you do all these problems, odd and even, I mean, you will have subjected yourself to so many different looks, whereby you're going to become very experienced. Okay, and there is no substitute for experience, and you get experience by working hard, all right, at something. All right, so here on page, what is this? Hold on a second, what page is this? Page 253, ladies and gentlemen, will begin. I do have several of these lined up that I would like to demonstrate. Most of them are even problems. But if you ever see one that you would like me to demonstrate, by all means, just let me know, and I'll be glad to entertain the problem. Because like I said, if you take your eyes and glance down through all these problems, you can see they're all a little different. Everyone's unique and a little bit different. And again, the only way you're going to get good at these is by doing a whole bunch of these. Okay. All right, and that's also true in calculus. When you get in there someday, as I'm in integral calculus or differential calculus, the only way you get good at the problems is by doing a whole bunch of integration problems or antiderivative problems or differentiation problems, because everyone's a little bit different there too. So just remember, there is no substitute for experience, and the only way you get experience is by doing a whole bunch of problems in mathematics, a whole bunch of them, as many as you can possibly fit into your schedule. All right, so let's try to do a couple of these on page 253, I believe I said, number 2. We will attempt this one. It says to prove that the secant of theta multiplied by the cotangent of theta is equal to the cosecant of theta. All right, so that's what we will try to prove. Now I have a question for you, ladies and gentlemen. Which of these two sides looks more complicated, the left or the right side?
Left side.
All right, so we'll work with this left side here. And again, we don't know that this equal sign even belongs in between here. I mean, we're going to try to show that it does. So we want to show that the left side is indeed equal to the right side for all angles theta. not just some specific value of theta, but for any angle theta, positive or negative. All right, so we have to prove that this equal sign belongs in between these two expressions. That's what it means to prove this identity. So we're trying to prove the following as being a valid identity. All right. So we're going to work with the left side, and ladies and gentlemen, do I have any hints as to how to get started in working with the left side to show that it indeed is the right side? Anybody can give us a jump start here? Remember, we have at our disposal all the basic identities that we've seen in the past. We can throw at the left side. So we can use all of these identities back up here, ladies and gentlemen. They're all at our disposal, the reciprocal ratio and Pythagorean identities. Okay, so what can we do with the left side? Anybody? Keep in mind those guidelines that I just read in that shaded box. One of the guidelines says that if nothing seems to be working, convert everything into what?
The basic identities.
Okay, the basic identities. For instance, secant theta could be replaced with what? What can I replace secant theta with?
1 over cosine theta.
So we'll turn secant and theta into its equivalent cosine expression, which is 1 over cosine theta. That is to be multiplied by the cotangent of theta. And the cotangent of theta can be rewritten how? Cotangent of theta.
Cosine over sine.
Yeah, we just use a ratio identity, knowing that that is the cosine theta divided by the sine of theta. Again, just a word of caution, make sure that when you use like sine and cosine or any trig function, you always have an argument. Don't just say cosine, ladies and gentlemen, this is no good. These are trig functions, so they need arguments. So you always want to put an argument in there, whether it's theta or beta or gamma or whatever, but you need an argument, okay? Don't just say cosine. All right, so we're working with the left side and we're trying to show that the left side is equal to the right side. Now we can see we're being asked to multiply a couple of fractions together, and we know that we can use our cross-canceling ability if possible. We can see that cosine theta divides into itself once and divides into this cosine theta once, and we're left with 1 over the sine of theta. But what's another name for 1 over sine theta? Just a cosecant of theta using a reciprocal identity. And so we have clearly shown that the left side is indeed equal to the right side. And so this has been proven to be a valid identity. Okay. That one makes sense, ladies and gentlemen? That was a pretty simple one. I think we've seen one of that caliber before in the past. So that should not be a shell shock there. All right, let's try another one here. So to page 253, we have a whole bunch of them here to entertain us. I'm going to jump down to number 14, one like number 14. Again, like I said, if you see one that you would like to see demonstrated, and if I do not choose it, by all means, let me know. And I'll be glad to, entertain it. I mean, I wish I had time to do all of these, but that is just not happening. Not in our time frame here. All right, so I'm trying to prove that this expression on the left side is equal to the equal to 1 on the right side for number 14. And obviously the no-brainer here is that the left side is the side you want to work with. Could you imagine trying to show that 1 is equal to this left side? That would be very difficult. And for that reason, ladies and gentlemen, we definitely want to choose to work with the left side and show that it is equal to 1. All right, can anybody get me started on the left side here? Any ideas as to where we would begin? Usually where to begin is usually the toughest part. That's usually true in life too, ladies and gentlemen. The toughest thing in getting something accomplished is usually getting started in getting something accomplished. For instance, you say you want to go to college and get a degree. You know what the toughest part of that is usually? It's actually getting up, going down and registering and getting plugged into a college and registering for classes. That's usually the toughest part right there. All right, help me with this left-hand side. Get my ball rolling here, ladies and gentlemen. What do I do here on the left side? Anybody? What can we do?
Cotangent of theta squared plus 1 is a Pythagorean identity that is equal to the cosecant of theta squared.
Exactly. That's a good place to start. Notice we can tap into one of our Pythagorean identities, realizing that cotangent squared x plus 1 is equal to cosecant squared x. We can use that. So therefore, yeah, I mean, why not simplify this expression aside to parentheses? Replace it now with cosecant squared x. Excellent idea. So this got replaced with cosecant squared x. Next move would be to do what now?
Cosecant squared of x is actually 1 over sine squared of x.
Reciprocal identity. Therefore, we really will have the sine squared of x multiplied by 1 over the sine squared of x. This guy sits over 1. And these are reciprocals of each other. Notice. So when you multiply reciprocals together, you always get 1. And so therefore, the left side is clearly the right side. Okay. So that has been proven to be a valid identity. Also pretty simple. It's simple once you use this Pythagorean identity. You know, there'll be times when you try to prove an assertion as being an identity. When lays on, sometimes you start something on one side of your expression and it leads to something that gets messier and messier and leads to nothing but chaos. Don't freak out if that happens. That's a very common thing. Sometimes you go down a path that leads to a dead end. Don't panic. All you do is just, you know, start over, erase what you've done and just start over with something else. All right. It happens all the time. All right. So knowing exactly where to start, that's part of the challenge too, especially if we've never proven identities before. And we're going to make mistakes. Okay. Some of us will strike out on a path that leads to nowhere. It happens. But don't worry about it. Just, you know, scratch that off and start over again. All right. So that one's done. Okay. One like number 18 here. We will attempt this one. So this is the sine of t to the 4th power. So the whole sine t functions being raised to the 4th power minus the cosine t function being raised to the 4th power, all divided by sine squared t times cosine squared t. We want to show that that is indeed equal to the right-hand side, which is secant squared t minus cosecant squared t. So we want to try to prove that this is a valid identity. What side would you be willing to work with? Anybody? What side appears to be more complicated looking?
Left side all day.
All right, let's go with the left side. So we have a big old fraction here on the left side, and the numerator of which is the difference between the two trig expressions, and the denominator is the product of two trig functions here. All right. So, ladies and gentlemen, the left side of this we're going to try to show is equal to the right side for all angles t here in order to prove this thing here. All right. Now, this is a problem whereby notice the left side already is converted into sines and cosines. And so we don't do that. And you know, how to begin or what can we possibly do here to deal with this? Anybody? But there will be times when you're gonna have to tap into your ability to factor polynomials back in algebra. And I know when I teach algebra, regardless of the level of algebra, I always stress to my students, if anything else, if nothing else, get good at factoring polynomials. That's a skill that will always come back to, haunt you in higher level math. And this is a point in time whereby that is going to be the case here. Okay. And so what we can do here, ladies and gentlemen, is if we look at the numerator here, okay, if we look at this numerator here, we can maybe think of it as being kind of like a polynomial from algebra. So let's just think of like sine to the fourth of t minus cosine to the fourth of t. Just think of this being maybe kind of like a polynomial of the form of like a to the fourth power minus like b to the fourth power. Do you agree? Where a is like the sine of t and b is the cosine of t. Now, do we remember how to factor this from algebra? Do we remember how to factor a to the fourth minus b to the fourth? This is a binomial. Happens to be the difference between perfect what? Anybody remember the difference between perfect squares? So recall from algebra, a squared minus b squared factors how? Haley, how would you factor a squared minus b squared from algebra? You remember?
Is it a plus b, a minus b?
A plus b times a minus b, exactly. The product of conjugate binomials. Okay, so using that from algebra, factoring the difference of squares, we can factor this difference of squares of a to the fourth minus b to the fourth, in the sense that this would factor into a squared plus b squared times the conjugate, which is a squared minus b squared. So that's how we can factor this. And because we can factor a to the fourth minus b to the fourth this way, we should be able to factor sine to the fourth t minus cosine to the fourth t in a similar way. So therefore, this numerator is going to factor into sine squared t plus cosine squared t multiplied by the conjugate, which is sine squared t minus cosine squared t. And all this sits over sine squared t times cosine squared t. Everybody understand what I've done so far? I just factored the numerator of the left side as the difference of squares. Well, that's just great. But ladies and gentlemen, it looks like we went from a rather complicated numerator to one that looks hopelessly much more complicated. And so what was the point of that? Anybody know why I did that? Can you help me with the numerator and simplify the numerator further? Anybody? How does this numerator simplify further? Anybody? Let me ask you this here. Austin, are you with us this morning?
Yeah.
Okay. What can I replace sine squared t plus cosine squared t with? What can I replace this with?
I'm not too sure.
Go back and think of your basic identity, your trig identities. Do you have your basic identities next to you, or do you have them memorized?
I do not.
I'll give you a hint. This is one of your Pythagorean identities here. Sine squared t plus cosine squared t is equal to what? Do you remember? It's one of your three Pythagorean identities.
No.
Okay, I'll tell you what. Hold that thought. Let's go back up. Hold on. We're going to go back up to our basic identities here, ladies and gentlemen. Way back up here, the beginning of section 5.1. Okay, now, Austin, do you see an identity in here that would enable me to replace sine squared t plus cosine squared t with something? Anything? What can I replace cosine squared t plus sine squared t with?
With 1.
1. Everybody see that there? Because this is a valid Pythagorean identity. We accept this as being a valid identity, so we can use it. So therefore, yeah, we can replace this quantity with 1. So therefore, our numerator collapses down to 1 times the sine squared t minus cosine squared t, and all that sits over your sine squared t times cosine squared t. Okay, good. All right, so we've gotten it down to this. Now we're trying to show the left side, remember, is equal to the right side. That's what we're trying to show here. Anybody have an idea as to what we can do next here? Anybody? What can we do next, or what should we do next with that left side? Anybody got an idea? Well, here's also something that's commonly used. I've discovered when trying to prove expressions are valid identities. It actually goes way back, ladies and gentlemen, to basic mathematics, if you can believe that. Recall this: if I got a plus b over c, do we all agree that I can rewrite this and split this up into the sum of 2 fractions, namely a over c plus b over c? I know we've all seen that before, right? In fact, in basic math, we go from right to left, correct? Adding these fractions together, we go back to what we had on the left. Well, you can go from left to right also. You can rewrite this fraction as the sum of 2 fractions. So ladies and gentlemen, that's what I'm going to do. I'm going to make use of this simple property from basic math. I'm going to split this up into 2 fractions. I'm going to put the sine squared t over my denominator, which is sine squared t times cosine squared t, minus, I'm going to place the cosine squared t over my denominator, which is sine squared t times cosine squared t. Now, by having done that, how does that help? Well, what reduces out here? What can I cancel out between the top and bottom of the first fraction here?
Sine squared t.
Sine squared t drops out, and we're left with 1 over cosine squared t, minus. Second fraction, the cosine squared t's reduce out to 1, and I'm left with 1 over sine squared t. Now, we've gotten to where we need to go, because we know another name for 1 over cosine squared t by our reciprocal identity, is we can say this is secant squared t. 1 over sine squared t is another name for cosecant squared t. And we are done. We have shown that the left side is indeed equal to the right side for all angles t, and we have proven this to be a valid identity. So here's a classic example that illustrates our ability to factor polynomials from algebra, factor the difference of squares in the numerator. Using a Pythagorean identity, replace this factor with 1, and then using a basic skill from our elementary mathematics in taking a fraction and splitting it up into the sum or difference of 2 fractions. By doing that, we were able to reduce each individual fraction, and we got our answer. Okay, so it brings back a lot of good memories. Any questions about that problem? Okay, so that one is proven to be valid. All right. Okay. Do you think it would be possible to use the right side of this expression, ladies and gentlemen, and show that it is equal to the left side? Do you think that's even possible? Well, it has to be possible, because the right side is equal to the left side. But I'll tell you, trying to show that the right side is the left side would be more challenging. So you can see that clearly the way to go is working with the left side as opposed to the right side here. All right. So sometimes you may choose the wrong side. That happens too, especially when sides have comparable level degrees of complexity. So, I mean, don't freak out if that happens. If it does, just scrap it and then, start working with the left side, start all over again. All right, so that was one like number 18. Let's see if there's any others. Please do look at some of these examples in this section too, outside of class. It's only going to strengthen your ability as to what's going on in the section. That was one like number 18, number 20. One like number 20. See, ladies and gentlemen, you can see that they're all different. Everyone's a little bit, different, and they're unique. And because of that, they warrant that we take, maybe a special approach on each one. And the only way you're going to get good at this is by doing a whole bunch of these problems. That's going to be the same thing in integral calculus or differential calculus, ladies and gentlemen. You're going to be confronted with a whole bunch of different antiderivatives that you are to confront yourself with. For instance, if you got something like this in integral calculus, and you're being asked to integrate this with respect to theta, that's a heck of a lot different, ladies and gentlemen, than if you have something like this, being asked to integrate this with respect to x. You see, these are all different. They're different. And the only way you're going to get good with integral calculus is by looking at a whole bunch of these, giving yourself as many looks as you can possibly take in. Because you learn all the tricks of the trade by doing a lot of problems. Okay, there's no substitute for doing a whole bunch of problems and experience. All right, same thing with identities. All right, this will also be the case in integral calculus or differential calculus. The more problems you do, the better you're going to become. And for that reason, when you're given the bare minimum assignment by an instructor, I would try to do problems above and beyond that assignment if you want to really get sharp. Heck, I remember when I was a student, sometimes there were not enough problems in the book. I wasn't satisfied. So I went to the library and took out other books and did more problems of the same type. And that really, sharpened my skills. So as I'm trying to prove this identity here, what side would you be tempted to work with? Left or right side? Left or right side?
I would do the right side.
Yeah, the right side does look more complicated than the left side. That's pretty obvious. Let's work with the right side. Okay, on the right side, now what is it we're going to try to do? We have reached a point of this problem whereby this is very challenging to know what the next step is. Does anybody want to go out on a limb and say what we can do with this right side? Don't feel bad if you don't see it. It's a challenging thing, ladies and gentlemen, especially if you've never proven identities before. This next step is probably the furthest thing from our thinking. But anybody want to take a wild guess at it? What can we do with the first move on the right side? Anybody want to take a wild stab at that? Okay. This is something else that is often utilized when trying to prove expressions are valid identities. It actually, believe it or not, goes back to basic math. If you have a fraction in mathematics, do you agree as long as you multiply the numerator and denominator of that fraction by the same number or quantity, you still have the same fraction? Heck, we did this back in basic math, didn't we? We're going to utilize this basic skill from basic math to help us with our situation here. But what do I multiply the top and bottom of this thing by? What do I multiply the top and bottom of this thing by? I mean, we can multiply the top and bottom by 1 over 1 or 2 over 2 or 3 over 3 or 4 over 4 or 5 over 5 or x over x or theta over theta. You can multiply the top and bottom by an infinite number of things over themselves and still have the same fraction. So the next challenging step is, what do I multiply top and bottom by? Well, the only thing that really works is we're trying to somehow tap into our known identities, such as our reciprocal ratio or Pythagorean identities. 1 plus sine theta, ladies and gentlemen, is not one of our basic identities. But I do know, ladies and gentlemen, that 1 minus sine squared theta indeed is one of our Pythagorean identities. Do you agree? Everybody see this right here? Ladies and gentlemen, how can I make 1 plus sine theta become 1 minus sine squared theta? What would I have to multiply 1 plus sine theta by to make it 1 minus sine squared theta? Anybody?
One minus
One.
sine.
That's right. That's the key. Believe it or not, this is the key, ladies and gentlemen. So we're going to multiply the top and bottom of this fraction by the conjugate of the denominator, which is 1 minus sine theta. You see, but this is not obvious. And it's especially not obvious if you never proven identities before. I mean, how many people would know to do this? That's why, ladies and gentlemen, the only way you're going to get good at these is by seeing a whole bunch of them done and trying a whole bunch of them. Now you see this trick here that's being utilized on this problem. You can remember that for future situations that are similar. Okay, so multiplying top and bottom by the conjugate of the denominator oftentimes gets you somewhere, or multiplying the top and bottom by the conjugate of the numerator sometimes takes you somewhere. All right, so now the numerator becomes cosine squared theta times 1 minus sine theta. I'm not actually going to multiply the numerators together here. I'm not going to actually distribute the cosine squared theta yet in here. I'm just going to leave it separated like this. Now downstairs, when you multiply conjugates together, recall from basic algebra that if you got a plus b multiplied by a minus b, the product of conjugate binomials always gives you the difference between the squares of the terms. That's always true. So the denominator is going to be nothing more than the square of 1, which is 1, minus the square of the sine theta function, which is to say sine squared theta. So now I've got my expression on the right side down to this. Well, that's just great. But where am I going with this thing, ladies and gentlemen? Trying to show the right side is the left side. So don't lose sight of your ultimate goal. Showing the right side must become this. Does anybody know what I can do with the right side now?
The denominator is the same as the identity that you have up in the right-hand corner. So you 1 minus sine squared of theta is actually equal to cosine squared of theta. Put that in, cancel out the cosine squared of theta in the numerator, cancels out the cosine squared theta of the denominator. Got 1 minus sine of theta is equal to 1 minus sine of theta.
That's right. That's exactly what's going to happen here. So I'm going to replace my denominator with cosine squared theta, because by one of our Pythagorean identities, that is true. This is true here. This is valid. So the denominator gets replaced with cosine squared theta, of which now cancels out with the cosine squared theta in the numerator, leaving you with 1 minus sine theta. And we've clearly shown now that the right side is indeed the left side. Okay. All right. So this is a problem that probably would be very challenging to just about everybody that never proved identities before. It brings into light the fact that, ladies and gentlemen, you can always take a fraction and rewrite it as an equivalent fraction by multiplying top and bottom by the same thing. You can always do that. And it also shows us then why we did that, because we can then tap into the Pythagorean identity to help us rewrite the denominator of this expression as cosine squared theta, which ultimately takes us to the promised land there. Okay. So now you've seen it. You've seen this trick here, whereby multiplying the top and bottom of this fraction by the conjugate of the denominator, it leads to where we need to go. So now you put this in your bag of tricks or tools, ladies and gentlemen, because you've been exposed to this now. So hopefully you can remember this for a similar situation as something that you can use. Okay. See, we're more experienced now, having seen this problem done, than we were before we seen this problem done. We are now more experienced. That's the only way you're going to get good with identities, is not by turning and running away from them. You'll never accomplish anything that way. We need to confront these things and try to do as many of these as we can possibly do. All right, that was number 20. Let's try problem 24, one like 24. They want us to prove that the cosecant squared of theta minus the cotangent squared of theta equals 1. And obviously you probably want to work with the left side when you first see this left side here, I mean, or when you see this thing, doesn't it kind of like, the first thing that comes to my mind is some sort of a Pythagorean identity, because I see trig functions squared here. So that's the first thing that pops into my mind, is using some sort of a Pythagorean identity. In particular, which one would we or should we use though to help us out here? Anybody want to help us out with this problem here? And usually, ladies and gentlemen, when you're trying to prove identities, there might not just be just one way to manipulate one side to show it's the other side. Sometimes there's different places you can start. All right. In other words, I could convert all this entire left side into sines and cosines and then go that way, go from there. Or you can leave things maybe in their present form and go from there. Anybody want to help us out here? What can I do? Think of the valid identities we have at our disposal, our Pythagorean identities. Which one could I use to help me out here to rewrite that left side?
Just add cotangent of squared theta to 1, and that will become a Pythagorean identity, so that cosecant of squared theta is equal to cosecant squared of theta.
Okay, so you're saying I change cotangent squared theta?
Yes, just
Okay.
add that to both sides so that.
Oh,
way
wait a
you
minute.
get rid of-
Oh. I'm glad you brought that up. Ladies and gentlemen, why can I not add cotangent squared theta to both sides of this thing? Why can I not do that? Jared, why can I not add cotangent squared theta to both sides of this thing? Why is that illegal?
Did you say my name, Professor?
Yeah, Jared, why is it illegal to add cotangent squared theta to both sides of this thing if we're trying to prove that the left side's equal to the right side? Why can I not do that?
Give me a hint.
Well, first of all, do we know for a fact that this equal sign even belongs in between the left and right side? Do we know that? I'll give you a hint. We don't know that, do we?
No.
Ladies and gentlemen, because we don't know for a fact that the equal sign even belongs between the left and right side, we're trying to show that. We cannot move things from one side to the other side. We could only move things from one side to the other side by adding or subtracting something from both sides, or dividing or multiplying both sides by something, if we knew for a fact this equal sign belonged in between here. In other words, if we have a valid equation, like if this is a valid equation, ladies and gentlemen, we know we can subtract 1 from both sides because we know the equal sign belongs in between here. We know this is a valid equation. Here we're trying to prove that this is a valid equation. Because of that, it's illegal to move anything from one side to the other side or do something to both sides. You cannot do that. All right, so does anybody, was it Sean? Do you want to maybe retract in your thinking and help us with this left side? How could I rewrite this left side using a Pythagorean identity maybe to help me ultimately show that's equal to 1 on the right side?
I can try, but that was really easy if I could just do it the other way.
Yeah, I
But-
know, that'd be great. But we're trying to show this equal sign belongs in here. So fight that temptation, ladies and gentlemen. Don't be adding to something to both sides, or subtracting something from both sides, or dividing and multiplying both sides by something. We're trying to show this equal sign belongs there. We don't know it belongs there. I'll give you a hint. We can use one of our Pythagorean identities to maybe rewrite either one of these as an equivalent form. Anybody?
All
know
right,
which
so what I would do now is that I would just break it down to 1 over sine squared of theta minus cosine, let's see, cosine squared of theta over sine squared of theta, and then combine those to one fraction so that it's 1 minus cosine squared of theta all over sine squared of theta.
Yep, this is definitely a valid way to show this identity, or to show that this is a valid identity, is to convert everything into sines and cosines. And notice now we have the difference of fractions that have the same denominator, so we can combine them like this and place this over sine squared theta. That'll work. And now notice the numerator is equivalent to what? from one of our Pythagorean identities, we know that sine squared theta plus cosine squared theta is equal to 1. We know this is a valid identity. The equal sign belongs here. So therefore, in this case, knowing this is a valid proven identity, I can subtract cosine squared theta from both sides. It's legal to do that with this one because we know this is a proven valid identity. And ladies and gentlemen, another name for therefore for 1 minus cosine squared theta is sine squared theta. So you can replace the numerator now with sine squared theta. And that divided by itself leads to obviously 1. And we have shown that the left side is indeed the right side. So we are done. We have proven now, therefore, that this is a valid identity and that equal sign does belong there. That's one way to having done the problem. There is another way. We could have manipulated the left side without converting things into sines and cosines. Does anybody see that way if I did not convert everything into sines and cosines? How we could have tapped into one of our Pythagorean identities to show that the left is 1? Anybody know how we could have done that?
Could you just replace the cosecant squared theta with 1 plus cotangent squared theta?
Exactly. Another way, ladies and gentlemen, is instead of converting everything into sines and cosines, which is perfectly okay. I mean, it works. It's a great move. Nothing wrong with this. But another way you could have done this is realizing that cotangent squared theta plus 1 is equal to cosecant squared theta. So another name for cosecant squared theta is cotangent squared theta plus 1. So another thing we could have done, okay, so another way we could have done this problem is I could have replaced my cosecant squared theta with cotangent squared theta plus 1, and then we're subtracting off the cotangent squared theta. And then you can see clearly by having done that, the cotangent squared thetas cancel out, leaving you with 1. And you could get your answer. Actually, this would be the quicker way to go. All right, but this method works equally well. Nothing wrong with this. So this is showing us there's going to be times whereby you can take more than one path to your destination in proving an identity. This path works or this path works. All right, but it has to be a valid approach one way or another. All right, so that one's done. That was one like 24. Okay, let's see, 950. All right. Ladies and gentlemen, one like number 26. This should bring up a deja vu. Well, let's see here. This should bring up back a deja vu, number 26. Does anybody know what I'm saying when I say deja vu for 26? We've seen this before in a problem earlier. Anybody remember what we did or what that situation was? What side would you want to work with, left or right side?
The right side.
Okay, you want to work with the right side. All right, let me think here now. If we work with the right side, what are we going to do? What are we going to do to that right side, ladies and gentlemen, to try to show that the right is equal to the left? What I don't like on the right side is we just have squared trig functions. On the left, we have functions to the 4th power. That is obviously something that has to be addressed. But what do we do? What do we do? Anybody? What to do? What to do? What to do? You know, you could multiply top and bottom of the thing by the sine squared of theta. That would give you sine to the 4th theta in the denominator. But in the numerator, we would have sine squared theta plus sine squared theta times cosine squared theta, which, where would we go from there? In other words, what I'm saying is, what if I try to multiply top and bottom of this thing by sine squared theta? That would at least give me my denominator, which is showing sine to the fourth power of theta, which is moving kind of like in the right direction because we got things to the fourth power over here. In the numerator, we'll have sine squared theta times 1 is sine squared theta plus sine squared theta times cosine squared theta. For now, all I can do is just say sine squared theta times cosine squared theta. So what I did was valid going from here to here, all right? But like, how does that help us? Let's see. Ladies and gentlemen, I want to ultimately show the right side is the left side. How to do that, or what can I do? Anybody know what we can do here? Let's see here. Anybody know what we can do with this numerator here? Let's see. So this is illustrating something that may occur to a lot of us, if not all of us, at one point in time. Sometimes you start off or strike off trying something, and it leads to something that appears to be getting more complicated and to a point whereby we don't know how to get out of the hole we're in. It happens, all right? It's gonna happen. So sometimes you may have to, maybe scrap an idea and start over. I don't know. I mean, what else can we do with this? I mean, you could rewrite maybe like one of these using your Pythagorean identity as 1 minus the square of the other function. For instance, you could rewrite maybe sine squared theta as 1 minus cosine squared theta. I mean, you could maybe do that. In other words, what I'm saying here is you could maybe rewrite this sine squared theta as like 1 minus cosine squared theta using one of our valid Pythagorean identities. I mean, nothing that says we couldn't do this, okay? And then you could maybe distribute this inside the parentheses, in which case we'll have sine squared theta plus cosine squared theta minus cosine. Now, cosine squared theta times cosine squared theta is cosine to the fourth theta. And that's good to see that cosine fourth theta surfaces. And we got this over sine to the fourth theta. That's good, I guess. Maybe. Now what? What can we do here, though? We still got our squared functions here. I could maybe rewrite this, ladies and gentlemen, as what? What can I how can I rewrite sine squared theta plus cosine squared theta?
Isn't it 1?
1. Yeah, we can replace this with 1 using our Pythagorean identity. So we got 1 minus cosine to the fourth theta over sine fourth theta. I mean, everything I did up to this point is valid. Every move was a valid move. Well, that's just great. Anybody know what we can do next? I'll give you a hint. It's something we seen earlier, a trick from basic math. Anybody remember? Involving fractions. Anybody remember that little basic thing? That little trick? Comes from basic mathematics, ladies and gentlemen. Involving fractions. Do you recall? See, that's why it's important to take see a lot of these done and to try a lot of these, because that's the only way you're going to get experienced in remembering things. Recall from basic math. Do you recall this? If I got a plus c over b, what did I do? Anybody remember? What can I do?
A over b minus c over b.
Well, in this case, yeah. If this was a minus, it would be a over b minus, c over b. Yeah. That basic property from, basic mathematics we can use here. We can split this up. I can put the 1 over the sine fourth theta minus cosine to the fourth theta over sine to the fourth theta. We can do that. You can always split this up on the difference of two fractions. You can use this property. Why did we use that? How does that help us? Well, what's another name for 1 over sine to the fourth theta? That's better known as cosecant to the fourth theta. What's another name for cosine fourth theta over sine to the fourth theta? Better known as cotangent to the fourth theta. And ladies and gentlemen, we have shown that the right side is indeed equal to the left side. Everybody see that there? We've shown that the right side is equal to the left side. So you know what? You can work with the right side and show that it's a left side. It worked. It worked.
Do you think it would have been easier to do the left side though?
Yeah, I mean, that's what I'm thinking. I mean, I'm staring at all these steps here and I'm thinking to myself, wow, I'm looking at the left side there and I'm thinking, wow, I mean, if we tried the left side, you think maybe it might have, involved a less number of steps here. And I'm going to show you that that is indeed the case, that is true. Ladies and gentlemen, why can I say, I'm just curious here, why can I say cosine of the fourth theta over sine of the fourth theta is cotangent to the fourth theta? Notice we've been kind of throwing that around loosely here. I mean, it seems like it would be, but why is that valid to even say that? We know, what do we know? We know for a fact that cosine theta over sine theta, we know this is equal to cotangent theta. We know that. What enables me to justify then, ladies and gentlemen, that the cosine of the fourth theta over sine of the fourth theta is cotangent to the fourth theta? Well, look, we know this is a proven identity. That's one of our ratio identities. So if I raise both sides of this equation, which is understood to be an equation because it's a proven valid identity, so this equal sign belongs here. If I just raise both sides of this equation to the fourth power, I'm doing the same thing to both sides of an equation, correct? And we were taught back in algebra that if you have an equation, if you raise both sides to the same power, you should still have a valid equation. So if I raise both sides of this equation to the fourth power, you can see why it's valid to say cotangent to the fourth, cosine to the fourth theta over sine to the fourth theta is equal to the cotangent fourth power of theta. You can see why it's valid to say that. Because this is valid, we can raise both sides of the fourth power, this must be valid. That's why you can say that this is indeed cotangent fourth of theta. Legal to say that. All right, how about that left side? Anybody know what we could do with this left side? If we were to do this problem over again, ladies and gentlemen, how can we prove, working with the left side, that we do in fact get the right side? And that's why when I first wrote this problem down, I said there's a deja vu thing here of something that we've done in the past on an earlier problem. Does anybody remember what that was? Oh, by the way, this has to be over sine squared theta. Hold on a second. This has to be over sine squared theta. Okay, does anybody remember what we did on a problem, a previous problem, which was about a half hour, 40 minutes ago? Anybody remember what I did with this left side here? I'll give you a hint. We went back to algebra and we asked ourselves, do we remember how to factor? There it is. The key word is factor. Do you remember how to factor the difference between what, squares? Remember that? Remember that little trick we used on another one? Well, that comes back to revisit us. So let's try to factor this left side as the difference of squares. So this left side should factor into cosecant squared theta minus cotangent squared theta times cosecant squared theta plus cotangent squared theta. So we can definitely factor the left side as the difference between perfect squares. Well, ladies and gentlemen, how does that help us? How does that help us now? I'll give you a hint. What can I replace this with using one of our valid Pythagorean identities? What is this really equivalent to? Right here. A Pythagorean identity. Recall, ladies and gentlemen, we have one of our Pythagorean identities that says cotangent squared theta plus 1 is equal to cosecant squared theta. Meaning that if I subtract cotangent squared theta from both sides of this proven valid identity or equation, which is legal to do now because this is an accepted proven identity, equal sign belongs there, we would have 1 is equal to the cosecant squared theta minus cotangent squared theta. So what can I replace this with? By this valid identity, Pythagorean identity, I can replace this with 1. So we have 1 times cosecant squared theta plus cotangent squared theta. Right? We can do that. And now, ladies and gentlemen, let's go changing the left side into sines and cosines. Another name for cosecant squared theta is 1 over sine squared theta. Another name for cotangent squared theta is to say cosine squared theta over sine squared theta. Then we can borrow a trick we've seen from an earlier problem. We can recombine these into one fraction. That comes from basic math, being able to do this. We have a common denominator, so we can write this as 1 plus cosine squared theta over sine squared theta. Ladies and gentlemen, we have shown that the left side is the right side, and we're done. So working with the left side, you can show that it's the right side. You have to know how to factor the difference of squares, though, from algebra. Okay. So whether you work, ladies and gentlemen, with the right side and show that the right side is the left side, or if you work with the left side and show that the left side is the right side, it's up to you. So just because you choose a side and it doesn't seem to be going anywhere for you, sometimes maybe by scrapping that idea and going to the other side and working with the other side, that might help. Both these sides appear to be almost of equal complexity, almost. So it's your choice there, whether you want to work with the right or left side to show it's the other side. Any further questions on that one? All right, as known like number 26 there. Let's see here. What else we got? Let's see, number 34. Okay. Ladies and gentlemen, one like number 34. We want to prove that the left side is equal to 0 for all angles theta. Does anybody know what side we would work with? Problem 34. I think this is a no-brainer. What side we need to work with? Obviously, anybody want to work with the right side and show that 0 is equal to the left side? Good luck on that one. I'm going to work with the right side and show that the right side is indeed equal to 0 for all angles x. So we're going to try to prove number 34, working with the left side. Okay, ladies and gentlemen, we're now confronted working with the left side where we have the difference between fractions. Anybody, can you give us a hint as to how to begin? Think back to basic math when you have the difference between fractions, or think back to algebra when you have the difference between rational expressions. These are not rational expressions, but this is analogous to the difference of rational expressions. You remember what you had to do, first of all, get a common what? Denominator. Notice both these denominators are already in factored form. Therefore, we should be able to put together our LCD. And I have a question for you. What would be my least common multiple or denominator of 1 plus sine x and cosine x? Anybody? What do I need in my LCD such that it would be divisible by both denominators? What do I need? What factors? What factors do I need such that it will be divisible by cosine x? We're going to need a what? Cosine x. What other factor do I need in my LCD so that it will be divisible by 1 plus sine x? We need a 1 plus sine x. So ladies and gentlemen, this would be your least common denominator of both these denominators, this entire expression. Now that we have our LCD, we're going to build these fractions up into equivalent fractions that both take on the least common denominator. So what do I have to multiply the top and bottom of my first fraction by to accomplish that? Anybody? Mark Brooks, are you with us this morning?
Yeah.
What would I multiply this first fraction by so that I build it up into an equivalent fraction where its denominator must be cosine x times 1 plus sine x? What do I multiply top and bottom of this by?
Cosine x.
Cosine x. So this take the top and bottom of the first fraction and multiply the top and bottom by cosine x. Got to multiply the bottom by the same thing though.
Mhm.
All right, so that one now is an equivalent fraction for the first fraction. Now the second fraction, okay, has cosine x in its denominator. It is missing what factor? It's
Sine.
it's missing the 1 plus sine x. So top and bottom of the second fraction gets multiplied by 1 plus sine x to build it up into an equivalent fraction that now possesses the least common denominator. All right. Cosine x times cosine x is better known as cosine squared x. The denominator I will just leave in, well, let's see, I'll probably just leave in factored form for now. Cosine x times 1 plus sine x. I won't actually distribute that in yet. The numerator, we have the product of conjugates, 1 minus sine x times 1 plus sine x. Recall is going to be nothing more than the difference between the squares of the terms. So it's going to be 1 squared or 1 minus the square of sine x, which is to say sine squared x. So again, when you multiply 1 minus sine x times 1 plus sine x, you're going to get 1 minus sine squared x. The denominator, of course, I will leave just kind of like in factored form. Well, that's great. I'm not sure where this is. I'm not sure where this is taking us, ladies and gentlemen. We do have a common denominator now, so we should be able to combine our numerators. So therefore, I can say cosine squared x minus, here's a big mistake. A lot of us are going to fall into this little pitfall. Ladies and gentlemen, we're not just subtracting off the 1 here. We're subtracting off this entire numerator here, this entire fraction. You need to enclose the second numerator inside parentheses because this 1 here needs to be distributed into both these terms. That's a common mistake. So it's subtracting 1 minus sine squared x. And all this sits over our common denominator, cosine x times 1 plus sine x. Well, that's great, but we're still trying to show the left side is equal to 0 here. Still not convinced. Well, let's distribute this negative sign inside the parentheses here. So therefore, we'll have cosine squared x minus 1. The opposite of a negative sine squared x is plus sine squared x. And this sits over your common denominator. Now in the numerator, notice we can get together, we can rearrange these terms in the numerator. And I can put the cosine squared x adjacent to the sine squared x and adding them together all over our common denominator. Now, how can I simplify that numerator? Anybody? Whoops, this should just be 1 plus sine x. How can I simplify the numerator? What's cosine squared x plus sine squared x by a valid Pythagorean identity?
That equals 1.
1. And what's 1 minus 1? 1 minus 1. 0. And ladies and gentlemen, 0 divided by anything is 0. We have shown that the left side is indeed the right side. So we got 0. So the left side is indeed equal to the right side, which is 0. So we have shown that the left side is 0. Okay. Left side is 0. So this is a case whereby you might have to get a common denominator in combined fractions, building up to equivalent fractions and adding or subtracting the fractions and then going from there. That happens quite a bit in proving identities. Must get a common denominator. All right, so I just wanted to show you that one there. Okay, ladies and gentlemen, so I think I've shown you enough of these to kind of like clearly indicate the situation we're confronted with in section 5.1. And I hope I have gotten or driven home my point of the more of these you do, the better you're going to become at these. I would try to do not just the odd problems. I would try to do every single problem in that section 5.1, odds and evens. I know that seems like a lot, but if you want to really get good at identities, I would do all of them. Okay, because you're going to give yourself a whole bunch of different looks in doing all of them. And that's the only way you're going to, fill or that's the only way you're going to populate your toolbox with all the tricks you're going to need to have at your disposal in proving expressions as being identities. Okay, so I would like you to do a couple problems for classwork today. And you guessed it, it's proving a couple of identities. So this is classwork for August 2nd. I want you to prove I'm on a couple of identities here. So problem number 1, I want you to prove that the secant of theta plus 1 over the tangent of theta is indeed equal to the tangent of theta over the secant of theta minus 1. I want you to prove this one. Oh, so we're all on the same page, ladies and gentlemen. I want you to work. I want all of us to work with the right side. So I want all of us to work with the right side so that we're all on the same page. Okay. That's problem number 1. And then problem number 2, cosine to the 4th power of t minus sine to the 4th power of t over sine squared of t. I want you to show that that's equal to the cotangent squared t minus 1. And I want you to work with left side. We'll all work with the left side for number 2. There you go. Let's see if you can do something with those. And we'll come back and look at those. So here's the solution to problem number 1 of the classwork. This is one way to show that the right side is equal to the left side. Notice I chose to multiply the right side by the conjugate of the denominator. The conjugate of secant theta minus 1 is secant theta plus 1. I leave the numerator in factored form, but the product of the denominator is secant theta minus 1 times secant theta plus 1. Recall from algebra, when you multiply conjugates together, a plus b times a minus b, you get the difference between the squares of the terms. So therefore, the denominator becomes secant squared theta minus 1. But les amis, because of a Pythagorean identity that we have at our disposal, we know this is a valid proven Pythagorean identity. Therefore, we can subtract 1 from both sides of this equation or identity and show that the tangent squared theta is equal to secant squared theta minus 1. So we can replace this denominator with tangent squared theta. Now this tangent will cancel out with itself and take out one of these tangent theta thetas in the denominator, leaving you with 1 over tangent theta times secant theta plus 1, which is indeed the left side. Number 2, it's probably best to factor the left side of that identity as the difference between squares. Cotangent squared t minus sine squared t times cosine squared t plus sine squared t. But another name for cosine squared t plus sine squared t is 1 by a Pythagorean identity. So we can replace this with 1. And therefore, our fraction collapses down to this. But now I can make use of that simple property of fractions from basic math. I can split this up into the difference of 2 fractions by placing each term over the denominator sine squared t. The first ratio is another name for cotangent squared t. And the second ratio reduces down to 1. And we have now shown that the left side is indeed equal to the right side for all angles t.